Okay, we shall continue our lesson. Okay, as you are aware that today they announced that our PKP is continuing until June 9th. So we have one more month more, roughly. Anyway, we will have ample notice before the school reopens. So I think we have to still continue our lessons as usual. Okay, as I've been telling you all the other day, we are going into a new concept today. Okay, the other day I just discussed the application of electromagnet, the application of electromagnet the other day. So today we are going into another subtopic. This is quite an important area also in electromagnetism, because this is where we are using the idea of force, that is a force created by this electromagnet. But the thing is slightly different, because we have two magnetic field to interact. Okay, as you all know that when you have two magnet, two pieces of magnet, one say north, one is south, when you bring them together, they will so the same pole they will repel. If it is the opposite pole, they will attract. That means there is a force is involved here when you bring the magnetic field closer. So that's the idea we're going to use here. And maybe it's quite important in the sense that, you see, if you look at most of the moving electrical, the applicable electrical appliances which is moving, like for example fan, motor, alright. So all these things are moving with the help of electricity. So have you ever wondered how this movement comes about? It doesn't matter whether it's rotating or moving straight or forward, doesn't matter, okay? As long as there is a motion. Okay, this idea of motion actually comes from interaction of two magnetic field. Okay, how these two magnetic field is brought is like this. One is from permanent magnet, another magnetic field is come from the current carrying conductor. Earlier we learned that in a current carrying conductor there is a magnetic field around it, which we can use Fleming right hand grip rule to show that the current direction and the direction of the magnetic field. So if you look at the title by itself, the force on a current carrying conductor. So here we have a keyword here, force, current carrying conductor in a magnetic field. That means current carrying conductor is one, current carrying conductor. Magnetic field is permanent magnet. But remember, current carrying conductor itself already got a magnetic field. We already learned earlier. So, and I told you just now, when you have two magnets, you bring close together, the interaction of the magnetic field gives you a repulsion or attraction force. So over here, current carrying conductor, it doesn't matter whether it's a temporary current. It's of course a temporary current. When you turn on the circuit, there's a current flow, so there is a magnetic field. If you turn off, there is no current, so there is no magnetic field in the conductor. So when you turn on the current, there is a magnetic field, and this magnetic field interact with the permanent magnetic field. That's why they say force. Force is one part, current carrying conductor in a magnetic field. So current carrying conductor already got a magnetic field, permanent magnet got a magnetic field. So when these two magnetic fields interact, it generates a force. So later they design such a way that this force can give you a rotational force or straightforward linear force or whatever. Okay, but important is the force is created from the interaction of the two magnetic fields. So as you can see here, you can refer at page 66, and this one is at page 66. So what we are interested here is now, these force, okay, force is a vector quantity. So these force move in which direction? That's what we have to know here. So we already know that when two magnetic field interact, there is a force created. Okay. So if you turn on this circuit, let's say I turn on the circuit, so the current, as you can see here, it moves from positive terminal, pass through, then come back to the negative terminal. Okay, so when this happens, okay, it is found that suddenly whenever you turn on, the wires start moving on. Alright, but if you change the direction of current, let's say you put the positive terminal over here and the negative terminal the other way, when the current goes this direction, Just now it was moving up, right? Now it will move down. Okay, why I say it's moving up and moving down, that is what we have been observed. Alright, so in this case, to determine the direction of the force, so rather than remembering it by heart, we can use a simple rule. We call it Fleming left hand rule. Fleming left hand rule. Okay, left hand rule. Okay, left hand. You can see here at page 66. Okay, so they already give you Fleming. So for grammar we write here Fleming, but the keyword here is the name. Fleming. 1M. 1M. Take note. Don't write 2M. You get no marks. Okay, Fleming's left hand rule. Okay. So how this Fleming left hand rule apply to determine the direction of the force in a magnetic field from a current carrying conductor? Okay, very simple. Here you have your left hand. It's simple. Okay, this is your thumb, the first finger, your second finger. Alright. So this finger, right, the second finger shows the middle finger actually shows the direction of current. Okay. Alright. And this indicates the direction of the magnetic field. And this indicates the force. The thumb indicates the direction of the force. So in this case, if you look, direction of the magnetic field, always remember, if you put your finger, this will be your north to south. Okay? North to south. So this is north to south. This is thumb, the direction of current over here, in between the magnetic field. The direction of current always inside the magnetic field, not this direction or this direction. You have to see what is the direction of the current in the magnetic field. So direction of current in the magnetic field this way. This is the force, so therefore it moves upwards. This is what is observed. Okay. If you change the direction of current the other way, okay. Let's say I change the direction of current the other side. So what happened? Magnetic field is still there, but I change the direction of current. So when I change the direction of current, the current move this way. So you'll find that conductor move downwards. So all must be perpendicular. It's 3 dimension. All must be perpendicular. Okay, as you can see here, direction of the force, direction of the magnetic field. Magnetic field usually use symbol B. Symbol B, and then this is the direction of current. So you can see here 90 degrees, this is 90 degrees, okay, and then this to this is another 90 degrees. Okay, so they are perpendicular to each other to get your maximum force. Actually you can reduce the angle, but the force will be less. If it is 90 degrees, you get a maximum force. So direction of current, direction of magnetic field, move upwards. So this is how we get the force from here. Alright? So if I change the direction of the current, it goes down. Similarly, if I change the direction of the magnetic field, okay, let's say I put here north, here becomes south, here become north, here becomes south, so this is the north-south. So let's say the direction of current this way, so the thing will go downward because I changed the polarity. But if change the direction of current, so only the north-south, if I change the direction of current this way, it will still go up. Alright, so whether you change the magnetic field, it moves downward, or you change the direction of current, it will move upward. So accordingly, alright. So if you change the direction of current without changing the magnetic field, then it will move in opposite direction. Without changing the direction of current, if you change the magnetic field, it will move in the opposite way. Alright. So this is how it is done. And to elaborate further, we can look it over here. Right, as you can see here. This is at page 67. Page 67, please refer. So first diagram. Look, this is a positive. The diagram is a bit blurry in your notes. Please highlight. Looking at this video clip, please highlight this is the positive terminal. Negative. So the current moves this way. So this is a bare wire. So the current passes here. It touches the freely hanging wire here. This is a simple wire which is hanging in between this conductor. So the current passes through in between the thing and then. So here it is moving downwards. The north and south downwards. I already told you this first finger move downward, the direction of the magnetic field. Okay, this is the direction of the current. Okay, magnetic field downward, the direction of current inward. So therefore the force is, as you can see here, the force is goes this way. Alright? Okay. So now over here you can see north and south is still the same in the second diagram, but I changed the direction of the current. Okay, so please change the highlight. The diagram is a bit blurred. So here now negative, positive. Just now here positive, then negative. Now I switch the direction of current. So how the direction of current goes is this way. So if you, and just now it was moving inward. Alright, this is called magnet. We call it magnet. Okay, means a pair of magnet. Okay, so here the magnet is over here. So north south this way, the current coming this way. So as you can see, the thumb this side. So when you change the direction of current, the direction of the force become opposite and changes also. Okay, over here, as you can see, here north south. Now the north is at the bottom, south is on the top. The direction of the current still same, same as this. So just now it was moving this way. Now the direction of current, but the magnetic field is upward. So as you can see here, north to south, upward. The direction of current this way. So according to the Fleming rule, the force is this direction. Okay. So this is how we get the direction of the force of the conductor. That means this conductor will start to slide, sliding. It will move this way. Okay, or just moving this way. So this is how the three directions according to the magnetic field and the direction of current. But now if you look at this, alright, if you look at this, okay, the direction of current this way, you can see positive, negative. So direction of current this way, and then, but if you look at here, the direction of the current is parallel to the magnetic field. Can you see? This is a magnetic field. Both are parallel. So whenever the direction of the current is parallel to the magnetic field, there is no force. They must be perpendicular. They must be perpendicular. They must have an angle between the magnetic field and the direction of current. If there is no angle, zero angle, that means there is no force. No force. Okay. So as you start to give an angle between the magnetic field and direction of current, the force starts to exist and it becomes maximum, and it's 90 degrees. Okay. So this is how we get the magnetic field from the current carrying conductor, which interact with the permanent magnet to give you the force. Okay, so in fact that's the lesson today. It's a very short lesson also, but I would like to discuss now how this force comes about from the drawing of magnetic field. Okay, all right. Let us see now how this force then. Let us now draw the magnetic field lines to show how this force comes about. It's rather interesting. Okay, you have to know how. Okay, now let's take this. Okay, the current is going this way. Okay, inside the board. Okay, if the current goes inside the board, what we draw? We draw cross. Because the arrow. Remember, we were discussing about the direction of current using arrow. So the tail part is here. So it means the current is entering. So when the current is enters, based on your right hand grip rule in this conductor, what is the direction of the field? Clockwise, correct? It is clockwise. So this is the direction of the field. Okay? This is the direction of the field. We draw three magnetic field around the current carrying conductor. Okay. So this is the direction of the field. Okay. This is the direction of the field. Direction of the field. Yeah. Draw the arrow. Okay. Yes. Okay. Sorry about it. Okay. So this is the direction of the field. Okay. Now I put a permanent magnet. Okay, so permanent magnet, that means current is wire is entering, right? There's a magnet here. This is a magnet. Okay, this is a magnet. It's say this is north, here is south. Okay, normally you know that magnetic field, we already also learned, it goes from north to south. Okay, it goes from north to south. Okay, so here the field goes this way. Right? Here also the field this way. Okay, please look carefully. This is the conductor which is carrying current. The upper part, it follows this direction from left to right. The bottom part from right to left, right? The magnetic field. Okay, as you can see here, the direction of the field from the permanent magnet and the direction of the field from the current carrying conductor, both are same direction. Okay, that means this field comes, it follows. Okay, the magnetic field comes here, it follows. Alright? Comes here, it follows. So here, the direction of the magnetic field from the current carrying conductor and the direction of the magnetic field from the permanent magnet, both are same direction. That means more forces. Alright, here also the same force, here's another force. So more forces here. Let's say 3 line of forces, here 3 lines. So you have 6 line of forces which is moving in the same direction. But if you look at the bottom part of the conductor, alright, this side, the magnetic field from the permanent magnet is opposing the magnetic field from the current carrying conductor. That means two fields when opposed, feel a line of forces. So when two fields oppose, the forces, the resultant force become less or 0. Alright, the same magnitude will become 0. 20 Newton, resultant Newton, 0, 0 force. If 20 Newton and 20 Newton, the resultant force is 40 Newton. So here stronger force, here weaker force. So what happened here? Higher force to the lower force, right? Greater force will overcome the weaker force. So the conductor start to move down. So the magnetic field here you get like this. Okay, you get like this. And this is because entering. Okay, so over here this field is not there, right? It's weak. This from north to south. So here the field is very weak. So stronger field to weaker field, force move down again. So this field is known as catapult field. We call it as catapult field. Okay, catapult field, or sometimes we call it as elastic field. Elastic field. You know, elastic and catapult means elastic, Okay, so this is elastic field. That means the field like rubber, like go, it's pulling and letting you go. So this is how we have to draw the line of forces or the field lines that current carrying conductor, and we can use again Fleming left hand tool to verify. Okay, you look. Current and magnetic field, north to south. Current is entering into the board, right board, 3-dimensional, and then the force is downward. So it confirms that, okay. If I change the direction of current, let's say I put a wire coming up from here, carrying the current this way, then the force will be upwards. Then your line of forces, okay, here is stopped now. So here the force now becomes weak. Okay, so this is the north, so the force will be, okay, goes there, right? Okay, so the force here weak, so here now the force becomes stronger, so weaker, so it moves upwards. Okay, this is when I change the direction of current. You also can change the direction of the magnetic field and drop. Okay, so please refer your page in your notes. You can check your notes, okay, at page 68. Okay, they've drawn for you the elastic field, but here it's not complete. Okay, they put both the field. Eventually the field will be like this. Just now, okay, just now I draw the field will be like this. It's on the top of the conductor. So this is the direction of the catapult field. Okay, the current carrying conductor. Okay, this is what it's supposed to know. So to conclude, when you put a current carrying conductor in a permanent magnetic field, the current carrying conductor will experience a force. The direction of the force is given by the Fleming left-hand rule. So you must know what is Fleming left-hand rule. It represents the direction of current carrying conductor magnetic field and a permanent magnetic field, and the resultant field give you the force. So these three fingers will help you to tell you which direction the force, or any of the two given, you can tell which direction is the current, if magnetic force and the permanent magnetic field. You can determine the direction of current, either one. So 3, 2 must be given. So usually permanent magnetic field given, direction of current is given, so you can determine the direction of the force. So this is what you're supposed to know, and you must know how to draw the force. Okay? The magnetic field line, the elastic field. So to further, you please look at your page 70, 69 and page 70. Try to draw the field for this. Now here we have two conductors, like the anchor here, alright? So the current one is entering, here it's coming out. Alright? Try to draw the field for these two, which I will discuss in the next class. So this is, once you know how to draw this, then we can explain how a motor works. This is a very simple, right? Simple single wire in a current carrying conductor. In a motor we have an anchor. We have an anchor. Alright, we have an anchor which is carrying current. So one force will be upward, one force will be downward, so you will have a rotational force. So you must know how to draw the elastic or the catapult field in a current carrying conductor for an anchor in a permanent magnet. So for that I want you to try. In the next class I will discuss that. Okay. So till then, please refer your notes and also my clip again. I will tell you that to get a better understanding. Then we'll discuss further. Okay. So in fact your notes they are drawn for you, which I just discussed. Look at the fields and see how to draw it. So you must know the direction of the force, the pattern of magnetic field, and the understanding. Okay, and the force of course depend on the strength of magnet, okay, and the magnitude of current. Okay, and if you have a thick wire or more coils, then number of turns. Okay, bin, alright. Strength of magnet, magnitude of current, and number of turns, or number of turns. Or let's say instead of putting one single wire, you put many wires the same direction. Okay, that means like a coil already. So when you have more wires, then more stronger the force is. Okay, so please revise the work and go through and draw the diagram, complete the diagram at page 68. I'll discuss in the next class. So till then we meet in another class. Thank you very much.